Hi everyone, and welcome to Hudson and Thames YouTube channel. Today's video is dedicated to cross-validation in finance and backtesting. My name is Illya Barziy, and I am a quantitative research team lead at Hudson and Thames. If you would like to discuss any of the contents of this presentation, either leave a comment under this YouTube video or feel free to message me in this social media. The contents of today's presentation are the following. We'll start with a brief introduction and we'll discuss what standard cross-validation is as a technique. Then we'll briefly cover how it can be used and applied in finance, the backtesting through cross-validation. In the very end, you'll be able to see some examples of use of cross-validation techniques with the MlFinLab Python package and the references section. In the references section, you'll be able to find links to the original literature sources to get a deeper understanding behind how these algorithms work and how they can be better used to solve your specific problem. Also, I would like to note that the link to this slide that you're seeing right now and that you'll be seeing throughout this presentation is present in the description under this YouTube video. So the introduction. The ideas covered in this presentation, as well as techniques, cross-validation, purge cross-validation, and combinatorial purge cross-validation are taken and well described in the book Advances in Financial Machine Learning by Professor Marcos Lopez de Prado. I highly encourage you to go and look at the original source to get a deeper understanding behind these methods and the reasoning behind these methods. So cross-validation, it's a tool to determine a generalization error of a machine learning algorithm and to prevent its overfitting. In financial machine learning, cross-validation can be used for the following, either for model development, say hyperparameter tuning, or for backtesting. Also, standard cross-validation techniques, unfortunately, have to be adjusted to be used in the area of financial problems. And if not adjusted, they can lead to overfitting and bad results. If you're interested in specific elements to be looking at from the book Advances in Financial Machine Learning, the description of standard cross-validation techniques is the chapter 7 of the book. Use case of cross-validation in backtesting is chapter 12 of the book. And even though not covered in this particular presentation, but if you want to get more information on the use of cross-validation in hyperparameter tuning, please check chapter 9 of the book Advances in Financial Machine Learning. I would like to also note that all the algorithms presented in this presentation are available out there in the MlFinLab Python package. And MlFinLab Python package is a great tool for you to use to create your own machine learning trading strategy. By getting the MlFinLab Python package alongside with production level code, you'll also get access to great documentation with a lot of use examples and links to Jupyter notebooks where there are more examples and you can play around with the algorithms hands-on. You get a deeper understanding behind the algorithms and how they can be used for your specific problem. To get more details on the MlFinLab Python package, either go to our webpage at hudsonandthames.org or contact the sales team with the application on our webpage. So the standard cross-validation. Cross-validation is used to split observations from an IID process into two sets, the training set and the testing set. And the most popular cross-validation scheme is the kfold cross-validation. It's well visualized in this example from the book Advances in Financial Machine Learning. This is a 5-fold cross-validation, and in each fold, the total number of observation is split into roughly 5 equal sets, 4 of them being used for training and the 5th used for testing. And what we can also see is that each observation in the test in each fold is present in one and only one set, either the training set or the testing set. This is to prevent the leakage of information from one set to another. Also, the outcome of this k-fold cross-validation is a k-by-1 array of cross-validated performance metrics. So in this case, this would be 5-by-1 array of performance metrics in this particular example. Now, about the use of k-fold cross-validation in finance. Even though many works declare that standard cross-validation and standard k-fold cross-validation work very well in finance, Professor de Prado argues and says that it's not actually true. And there are a few reasons why k-fold cross-validation actually fails in practice when used on financial problems. One being that the observations cannot be assumed to be drawn from an IID process. And the second one is the testing set is used multiple times in the process of developing a model, meaning that one can actually run a lot of runs on the k-fold cross-validation and optimize the results to this exact data set. So previously mentioned the leakage. And the leakage appears when the training set contains information that is also present in the testing set. This may happen either because the feature is serially correlated or the associated labels are derived from the overlapping data. Meaning that if in our testing set, in some of the labels, there is information that is gained from the elements present there in the training period, then we have a leakage of data. Also, leakage can lead to false enhancements in performance for both good and valuable strategy, but also for bad ones. And this is particularly a problem in the case of irrelevant features, because if there is a leakage present in the model which has irrelevant feature, the model may show that these features are actually valuable, and this may lead to false discoveries. So how the problem of leakage can be solved? The product proposes the following two methods to reduce the likelihood of leakage. One would be to drop the training set, drop from the training set any observation where yi is a function of information used to determine yj, and j belongs to the testing set. Meaning that if there is in a testing set yj, which was calculated as the function of set of observations from the training set, those elements from the training set have to be removed. Also, point 2 is to avoid overfitting the classifier. In this case, even when the leakage occurs, the classifier cannot use it to its profit. And the following solutions are provided: either use early stopping for the base estimators or bagging of classifiers. Now to cross-validation for finance. And the solution proposed in the original work is the purged kfold cross-validation, which consists out of adding two new ideas, the idea of purging and the idea of embargo. So purging, as described by the Prado, the goal here is to purge from the training set all observations whose labels overlapped in time with those labels included in the testing set. Meaning that, again, as described previously, if in the testing set we're having set of labels or information which was calculated based on some set of elements from the trading set, those elements from the trading set have to be removed or purged. Also, the idea of embargo. Financial features often incorporate series that exhibit serial correlation. Therefore, the observations that immediately follow an observation in the testing set should be excluded from the trading set. So, additionally, if what we're seeing is that the trading set comes after the testing set, some of the first observations from the trading set have to be removed. And this process is called by the Prado as an embargo. Here is a deeper look into how purging works. So we're having a train set, a test set, and then again a train set, and we're having two elements of overlap. So the leakage occurs if there is an information overlap, as right here, between observations, or if the labels of these observations are concurrent. And the logic behind purging, the logic is to purge observations with overlapping labels, meaning that the labels from the testing set are obtained based on any of the observations from the testing set. Essentially what we described previously. A deeper description behind how this is done is in the part 7.4.1 from the original book. Also, how to determine if the leakage occurs and if purging actually helped us. So, as described, when leakage takes place, the performance improves merely by increasing K. But in many cases, the purging is sufficient to remove leakage. And the sign of it is the performance after purging, will improve only up to a certain value K asterisk, after which it will not be improving, meaning that the backtest is not profiting from leaks. And here is the description behind the idea of embargo. So even though we have overlap here and here, additional embargo period is being added here. And the embargo is used on training observations that appear only after the test set to additionally prevent leakage. How it's implemented is by extending the right side of the restriction before purging. And for exact description, I'm referring to part 7.4.2 from the original book. Usually the embargo value H equal to 0.01 T, where T is the total number of observations in our data set, is sufficiently to prevent all leakage. And this can be confirmed as the performance does not improve indefinitely by increasing K after the embargo. Now, backtesting through cross-validation. So backtesting, according to the Prado, can be described as follows. A backtest evaluates out of sample performance of an investment strategy using past observations. And the past observations can be used in two ways. One here would be, in a more narrow sense, is simulating the historical performance of an investment strategy if it had been run in the past, meaning that we're taking a part of information taken from the past, training model on it, and then testing it on the data from the future that model didn't previously see. This is called a walk-forward method of backtesting, and it's very widely used. But in a much broader sense, backtesting is assessing how the model would perform on a previously unseen data, or in the case when the model was trained on one set of data and then tested on another set of data. And this does not strictly imply that the training data should come from the past and the testing data should come from the future. Therefore, the cross-validation technique can be used in backtesting. So the first one here described approach is the walk-forward method, and the second one is the cross-validation method. Now let's briefly look into more detail into the walk-forward method. It is the most commonly used backtest method in literature. It has its set of advantages as well as disadvantages. So the advantages are the following. One is that it has a clear historical interpretation, meaning that, yes, we're taking a set of observations from past, train a model on them, and then assess how the model would perform on the previously unseen set of observations from future, as it would happen if we would be following a historical line of events. The second advantage is that since the history itself is a filtration, as long as purging is implemented, there will be no leakage, meaning that we don't have to add restrictions such as embargo, because we never have model trained on future data points and then tested on previous data points. It also has a set of disadvantages, though. So first one is that only a single scenario is tested that is very easy to overfit, meaning that as the backtesting goes, we're having only one scenario and multiple runs can be done on this scenario to obtain better results for this exact testing data set. Second, it's not representative of a full performance, as the results may be biased by a sequence of data points. In this case, what's meant is that there might be a particular set of events in our testing data set that are well for this particular set of strategy. And even though the backtest may actually be good and be performed once, what we might see in the future is a worse performance. And the last one is the decisions are made on a smaller portion of the total sample, meaning that we're having a part of the data used for training and a part of data, usually a smaller one, used for testing. And therefore, we're making our decisions on the performance of the strategy based on the smaller part of the total data set. On contrast, here is the cross-validation method. And as mentioned previously, the historical accuracy here is not the goal, but the objective is to test the strategy performance on data unpreviously seen by the strategy. It also has a set of advantages and disadvantages. Let's briefly discuss what are they. Advantages. So not one, but k scenarios are being tested. In the event of kfold or purged kfold cross-validation, actually k scenarios being tested, meaning that we're having k performance measures of such strategy. Also, the decisions are made on sets of equal size. So since the original data set is split into roughly same chunks of data, and the information in these chunks of data is roughly equal, we're making decisions based on those k roughly equal parts of performance outputs. Also, the advantage is that right now, every observation is a part of one and only one testing set, meaning that right now we're utilizing each element in our data set to generate the performance metric. It also has a set of disadvantages, though. Only one forecast is generated per observation. So even though we do have forecast for each observation, it's only one forecast. And in reality, we can have multiple forecasts for each data point in our data set. The second one is that it doesn't have a clear historical interpretation, meaning that it can never actually historically happen that we're training a model on future data, and then we're able to actually test it on past data with the training abilities. And lastly, the leakage is possible, as the training set does not trail the testing set. And the solution to this, proposed by Professor De Prado, is the combinatorial purge cross-validation. It's presented to address the main drawback of the walk-forward and the cross-validation methods, having a single path. So in walk-forward, we do have the one backtesting path and the results of backtesting only on a subsample of data. On cross-validation, we do have performance metrics per each data point in our data set, but this is always a single path. So in combinatorial purge cross-validation, given a number of backtest paths, it would generate a number of training and testing sets needed to generate those paths, purging observations that contain leaked information. And also additionally here, embargo can be added. For the full description of how this algorithm works, I encourage you to check part 12.4 from the original book. So the example here below would show the composition of train test splits if we're having 6 groups in total, out of which 2 are used for testing purposes. Say we have our data set, which is split into roughly 6 equal groups. So G1, G2, G3, G4, G5, and G6. And we're seeing, and 2 of these groups will be used for testing purposes. Then we have from S1 to S15, 15 total combinations of how the original data set can be split into the testing, into training and testing subsamples. So for example, in S1 for training, G3, G4, G5, and G6 will be used, and for testing, G1 and G2. For S7 for training, G1, G3, G5, and G6 will be used, and for testing, G2 and G4, which would allow us to get multiple paths per each data point in our data set. Let's look at the following explanation. So this shows the assignment of each tested group to one backtested path. So path 1 would be a result of combining the forecasts from the following elements. So G1 S1, G2 S1, G3 S2, G4 S3, G5 S4, and G6 S5. This would mean that we're having already one path of backtesting performance for all the data set that we have. And the path 2 would be G1 S2, G2 S6, G3 S6, G4 S7, G5 S8, and G6 S9. And here we're having the second path of performance per each data point in our data set. And in total, this is 5 paths. So for each element in our data set, we're being able to use it, in this case, 5 times to generate backtest performance. In the Prado in Advanced Financial Machine Learning, part 12.4, you can find many more details and grounding behind how the largest number of paths can be achieved using this method and at which expense, use examples, and also a theoretical backgrounding behind how this method addresses the backtest overfitting. Finally, I would like to show you how cross-validation techniques can be used when taken from the MlFinLab package. So here are the main classes and methods implemented in the MlFinLab package that can be easily used for cross-validation, either in finance or for backtesting. The purged kfold class is an implementation of purged kfold cross-validation with purging and embargo. It's an adjustment of the kfold from sklearn. Combinatorial purged kfold class is the implementation of the method that we've just described, the combinatorial purge cross-validation. The ML cross-val score function is the machine learning cross-validation score function. It's the function for cross-validation evaluation with sample weights and custom cross-validation generator. Cross-validation generator in this case can be combinatorial purged kfold, or the standard kfold from the sklearn. Also, the above elements have their stacked versions, meaning that the input can be actually multiple pairs of observations and labels, and the output will be a dictionary with set observations and labels split into testing and training periods, which can be useful for various purposes. First, let's see how one can apply standard kfold, and this is taken from the sklearn. We're having a set of labels, set of observations and set of labels taken from chapter 3 of the book Advances in Financial Machine Learning. And we'll be using random forest classifier with the kfold cross-validation measure, and we'll be checking the cross-validation scores. These are the parameters used for random forest classifier. In kfold, we're taking 10 splits of data and then applying the ML crossval score from MlFinLab to check the scores. Our output will be, in this case, 10 scores, as we're having the 10-fold cross-validation, and the accuracy in this case is 0.45 with the respective standard deviation. Now, this would be the output if instead of the sklearn cross-validation, we would be using purged kfold. So not the standard kfold, but the purged kfold. The inputs here for the random forest classifier will be exactly the same, but in purged kfold, what's already implemented is the idea of purging, and the second is we're adding embargo of 0.01. As described previously, this value should be sufficient to prevent any additional leakage in this case. And we're seeing that the output scores are still 10 values. However, the accuracy is right now lower with lower standard deviation, indicating that by adding purging and adding embargo, we're being able to actually get a bit more accurate results than the ones getting from the standard kfold from sklearn. And finally, here is the combinatorial purge cross-validation, also imported from the module cross-validation from MlFinLab, with the same input parameters for the random forest classifier, but in combinatorial purged kfold, we're using 10 splits, so splitting the original data set into 10 roughly equal subsets, and using 2 of them for trading. So in the example that we showed previously from the original book, we had 6 splits and 2 of them used in training, and here we have 10 splits, 2 of them used in in testing. Also adding the embargo of 0.01, and the idea of purging is also implemented in this method. We're having a set of scores with a set of accuracies. And in this case, instead of having just 10, the output is 45 scores, meaning that we have more than 4 paths for each observation. And the accuracy is lower with in comparison to the standard kfold, but additional to a lower standard deviation of these observations. And also, as described in the original book, if this method would be used actually in checking if there is overfit when reporting paper results, it would be much harder to falsificate the results and much harder to produce to claim that actual false strategies are valuable strategies. Here is a list of references. If you'd like to check the original sources, as I said again, for deeper understanding behind the methods and how they can be used in your specific case. I thank you so much for joining me in this presentation. I hope it was useful for you. If you have any questions, please either leave a comment under this video or feel free to message me under this social media. I again thank you so much for your attention. If you like this video, consider leaving a like and subscribing to our YouTube channel for more content. Thank you so much for your attention. Have a good day. Bye.